Maria, glad to be here today and welcome to everyone. And as Maria mentioned, my name is Marianne Walk. I'm the director of the National Energy Technology Laboratory, which is one of the 17 Department of Energy national labs and one of the 3 national labs that focus on applied energy technologies. Prior to joining NETL in February of this year, so I've been here only about 5 months, I was the Deputy Lab Director and Chief Research Officer at Idaho National Laboratory, which is the nation's designated research and development laboratory for nuclear energy development. So I'm happy to be here today with 3 nuclear energy experts from INL to discuss nuclear energy and its role in the clean energy economy of the future. So I'll just make a couple of very general remarks and then turn it over to each one of the panelists to introduce themselves and their topics. So as you probably know, nuclear has provided the United States with low carbon 24/7 power for decades. The nuclear fission process does not release any carbon dioxide or greenhouse gases into the atmosphere. And it currently provides almost 20% of the nation's electricity and about half of the nation's low carbon electricity. Nuclear's safety record is excellent, and its capacity factor, which is a measure of how often it is up or down, right, is by far the best in the industry at 92 to 93%. As a comparison, the capacity factor for electricity generated by a natural gas combined cycle plant is around 55 to 60%, and renewables such as solar and wind are lower than that. Nuclear, like coal, natural gas, and geothermal, uses heat to create steam to turn turbines to create electricity. That, of course, means that the heat has the potential to be used for additional uses, such as driving chemical reactions or making hydrogen or potentially chemicals. Nuclear has faced economic challenges. Large plants require major capital investments, and they're very expensive to build. And recent analyses, such as the DOE Pathways to Commercial Liftoff report for advanced nuclear that the DOE has published, suggest that the US will need more than 500 gigawatts of additional clean, firm electricity to achieve net zero in the next decades, and that nuclear is a proven option to deliver a good portion of that amount of clean electricity. While it has a lot of advantages, it's important to acknowledge some challenges and hurdles to achieve substantial new nuclear in the US, included our large capital investments for both large-scale nuclear installation, but also development and implementation of some first-of-a-kind new reactors to provide flexible power and heat. And our panelists will be talking about that. And despite nuclear's demonstrably excellent safety record, there is still public concern about safety that is expressed often. And while interim storage is also safe and effective, the final disposal path for spent nuclear fuel in the US does remain uncertain at this time. So here today to talk about all these aspects in more depth than I just mentioned are 3 experts from Idaho National Laboratory. We have Christine King, the director of the Gateway for Accelerated Innovation in Nuclear program of Department of Energy, which is hosted at Idaho National Laboratory. Dr. Shannon Bragg-Sitton, who is the Division Director for Integrated Energy and Storage Systems at INL, and Dr. Aaron Searcy, the Chief Technology Officer for INL's Nuclear Science and Technology Directorate. So welcome to each of you. And let's get started by asking each of you to briefly introduce yourself and make some opening remarks before we ask some questions. So let's start with Christine. I'll turn it over to you. And Christine is coming to us from her car while she's on vacation. So enjoy, Christine.
Thanks, Marianne. I'm actually glad to be here. I'm calling in from Big Sur, California. I have my hat on to cover my camping hair, and I brought a Zoom shirt with me. So I lead the Gateway for Accelerated Innovation in Nuclear at the labs. I've been with Idaho National Labs for 4 years. And prior to that, I spent 27 years with the existing fleet. And so really my expertise is about the private-public partnerships and how we make sure that the expertise we have in the national labs and the Department of Energy are used and useful as we pursue a new nuclear fleet. With that, while you might hear a lot about the reactors, which you see in the upper right-hand corner here, you'll see there's different sizes of those reactors. And I think Shannon's going to spend a little bit of time as she talks about integrated energy systems as in terms of how each one of those might work with different applications. It's important to understand, as Marianne mentioned, that there's a front end and a middle, it's a parallel system and a back end. So the front end is the mining of the uranium, the enrichment of the uranium, and fabricating the fuel that goes into the reactor. A big thing that's going on in this space right now is we have received historically a lot of our enriched uranium from Russia. And given the invasion of Ukraine, we are now working to domesticate a lot of that enrichment and also do more enrichment partnerships with our allies. Along with the lower left-hand corner, we did a study a couple of years ago in GAIN looking at what it would take to actually build the number of reactors. So if you think that we need 300 gigawatts of nuclear to reach a clean economy in 2050, and you build them at 300 megawatts each, that's like 3 reactors to every large reactor we have today. So that's a lot of, they're smaller components, but still a significant number of them that needs to be built. What was interesting in this report, it wasn't about the know-how of how to do it. It was really about the financial decision of when do you invest in your facility to upgrade and expand, and where will the workforce come from. The lower left-hand corner is our existing fuel cycle. We have a once-through fuel cycle, which means that the fuel goes into the core. It spends about 6 years there in our existing fleet, and then it moves into interim dry storage on site, eventually consolidated storage, and then a permanent disposal. We could go to the next slide. So this is our existing fleet. Our existing fleet is responsible for 20% of the generation. We should have edited this. Well, we have 94 operating reactors today, and we have 1 in Michigan, Palisades, that's looking at a restart. And that's an activity that's funded under the Loan Programs Office with DOE. But you can see here that while we're responsible for 20% of the generation, we're nearly 50% of the carbon-free energy in the United States. The kind of busy chart on the right-hand side, though, gives you an idea. The left-hand bars in each column shows you the current licenses for our fleet. If we do not extend the licenses of our current fleet, we would be retiring most of them by 2050. The blue represents the planned changes for license extension to 80 years. And right now we are seeing about 2/3 of the fleet are committed to extending their licenses to 80 years. The orange bars represent what it might look like if we were to extend all of the operating reactors to 80 years. And the numbers in the little chart there basically give you the gigawatts. If we, in that middle scenario that I talked about, we would be retiring 40 gigawatts of nuclear. So that only adds to the problem if we have to, if we're not extending. I will say that license extension has been going quite well with the NRC. So I expect that over the next few years, we'll actually be looking at the set of orange bars. Let's go to the next slide. Okay, so why is nuclear so cool? Nuclear is so cool because it's a very energy dense power source. A uranium pellet that goes inside the fuel rods is about the size of a gummy bear, and it is equivalent to 1 ton of coal. So if we go to the next slide, we start with a fully fueled reactor, and we to generate 1 gigawatt of electricity, we normally take 1 square mile of land. To generate the same amount of electricity with utility scale wind turbines, solar panels, you can see there the significant change in terms of land use. This is not to say that one is better than the other, but there is an optimization opportunity by pairing nuclear energy with renewable sources, where it gives us the opportunity to make the best of the resources that we have in the areas in different regions of the country. And I believe both Shannon and Aaron will touch on those items as well. And let's go to the next slide. So where is this happening? In the United States, there are 37 projects that have been identified. 1/3 of those are microreactors, and 25 of those are the small modular reactors. So thinking around 300 to 500 megawatts. The micros are running 20 to 50 megawatts or less. 18 of these projects have deployment dates prior to 2030. We are not going to have 18 new reactors by 2030. However, with this many in the pool, we do believe that we will have 5 to 10 or more by 2030. And that's important because for every one we build, we drive the risk curve for financial investment down. In terms of what's going on in the states, if we go to the next slide, many states have initiated or already completed feasibility studies or have open working groups. You can see the blue states that have completed their studies, and then you have the green states that have ongoing studies. If you're interested in seeing any of these studies, I'd be happy to provide the links to you. And with that, I'm going to pass it over to my colleague, Shannon Bragson.
Thank you, Christine, for such a great introduction. And thank you to C3E for the opportunity for us to talk about this really, really important topic that we're also so excited about. And we want to bring this to you today. I've been at Idaho National Lab now for almost 14 years. That kind of surprises me when I say it out loud. It's been a while and it hasn't seemed that long because I've been able to do some really cool research and development around all different types of nuclear technology, from ultra small space nuclear power systems to advanced fuels and down to the microreactors and really interesting deployment options in integrated energy systems. So we have a lot of capabilities being developed and that are already deployed that I hope we can share with you today. So if we go to the next slide, just building upon what Christine talked about a little bit, historically, decades ago, we saw the US select water-cooled fission reactor technologies to support power generation. Why was that selection made? Well, it was primarily because the US Navy was developing reactors for submarines, and they chose water-cooled technologies. So the commercial power sector was able to leverage significant investment in design, materials, fuels development in order to deploy commercial power using fission technology. A focus on economies of scale also led to decisions to develop large-scale, gigawatt-scale systems like you see on the right-hand side of this slide that can support centralized power generation. There were other developments in the works decades ago as well, looking at alternative cooling technologies, alternative fuels, and different sizes of reactors. So while we see good logic in why these large-scale water-cooled systems were selected, new technology developers are really reevaluating those choices such that these reactors of tomorrow can better meet a range of market needs, whether that be centralized generation with large-scale systems or with small modular reactors deployed with 6 or even 12 units at a single site, giving a lot more flexibility in how those systems might be utilized. And it allows us then, or even very, very small systems for remote locations or dedicated applications at industrial plants. having a suite of options like this really allows us to right size the technologies to meet specific applications. And those might be electrical applications or heat applications, and we'll talk a little bit more about that. It also helps these systems to be more on par with other generators on the grid, such as wind or solar installations. And to have the capability to support microgrid installations or distributed energy systems that feed a centralized grid. So we do have many other technology options now to meet what we need. And many of these advanced reactors also use different coolants and different fuels, and this allows them to operate at higher temperatures. Higher temperatures mean higher efficiency, both in electricity production, but also in delivery of high quality heat to industrial customers that may currently rely on the combustion of fossil fuels. So if we switch to the next slide, please, we'll start talking about what are our goals? What are we trying to achieve? Well, we have really aggressive goals that are being set out by the federal government, regional municipalities, and private entities, private industry, to achieve net zero solutions by 2050. And what that means is no emissions from electricity, no emissions or net zero emissions from industry and from the transportation sector. And we are looking at those resources that we have available to us and represented here to identify opportunities to more efficiently use those plants that we already have online that Christine spoke to, but then also the next generation of technologies across all of the non-emitting generation options that we have available to us. When we look at these aggressive decarbonization goals, we truly don't have the luxury to just stay in that upper right-hand corner of this slide and work just with wind and solar and hydro. We have to look across the board and look at other clean generation assets like nuclear energy that can help us to meet those goals across all of these different application sectors. When we think about these options for system designs, we need to realize that nuclear energy primarily produces heat. When we have fission that happens, the primary output is heat, not electricity. We actually convert that heat to electricity, and if we have losses, we have efficiencies that we have to take into account. But we can instead use heat directly to support many of the applications that you see along the bottom of this slide to decarbonize key areas of industry. Now, when we use that heat directly from a nuclear fission system, we do need to incorporate secondary or even tertiary loops into the system design to ensure that we have full isolation of the nuclear primary side, the fission system, from those downstream heat users, which might be producing products like hydrogen or chemicals or even fertilizers for the agricultural sector. And we need to ensure that we have isolation of the nuclear and the non-nuclear components. We need to remember that nuclear energy is also dispatchable, meaning that we can produce energy regardless of the weather, and we can take advantage of that and manipulate how we deliver energy to the grid and to these other applications as a function of when those renewable energy sources might be producing sufficiently to meet grid demand. So instead of curtailment, we can begin to look at opportunities for redirecting energy or a dynamic energy delivery system as opposed to curtailing those energy sources. And as noted by Mary Ann, we have an incredible capacity factor for nuclear energy at greater than 92% across the US fleet. These are assets that will help us to meet a broad array of energy demands without emissions. So when we look at these characteristics that nuclear power provides, we can see paths to a reliable, resilient grid that leverages all of these generation assets and a solution to provide other energy currencies like heat, hydrogen, and then utilizing carbon that can be captured and closing that carbon cycle to meet these industrial energy needs for both power, heat, and other feedstocks that drive these processes. So just summarizing that a little bit, when we have sufficient renewable production available to meet grid demand, that energy from the dispatchable nuclear energy resource in that same grid balancing area, or perhaps coupled within an energy park, can be redirected. Rather than curtailing it or just sending it to storage, we can redirect that to produce clean hydrogen molecules. We can use that clean hydrogen and captured CO2 to produce synthetic liquid fuels that now have a lower carbon footprint than traditional diesel and jet fuels in that heavy duty transportation sector. We can use that heat, hydrogen, and electricity that would otherwise not be present or curtailed for the chemicals manufacturing sector, metals manufacturing, steel manufacturing, and that fertilizer production to help support agriculture. So by considering all of these energy solutions in parallel, we can find potentially more efficient solutions from the perspective of energy utilization, so avoiding underuse of installed capacity. By redirecting energy to a variety of processes, we can achieve system cost efficiencies, where system cost is referring to the total cost of providing electricity to customers, not just the cost of that generation asset, but the interconnections, the transmission, the storage components. And we can find synergies across these technologies to reduce system cost. And we can also look to efficiencies in resource utilization, meaning utilization of the nuclear fuel and using that as much as we possibly can, taking advantage of that high capacity factor, but also land use and considering the land requirements for each of these technologies, and utilization of critical materials, such as those materials that are needed for energy storage components or solar photovoltaics. And we can really begin to understand how to minimize impact to the environment while maintaining reliability and resilience. So I will stop there, and I look forward to our discussion. Thank you.
Thank you, Shannon. Aaron is now going to make some remarks about the role of the Department of Energy labs and some of the projects that are going on at our labs.
Yes, thank you. So I've been at INL over 15 years, which, like Shannon, it just shocks me to say. I actually joined Idaho National Lab as a bioenergy researcher of all things. My passion for mitigating climate change led me to that field. And as I learned more about nuclear, I got really excited and wanted to get more engaged in that program. And what better place to do that than the lead Department of Energy Nuclear Energy Lab. So as Marianne mentioned, there's 17 national labs. The role of the national lab system is to do research for the public good while not competing with industry, which I'll talk a bit more about. But we engage with academia, with other national labs, with industry to advance science and technologies. So there's a variety of different types of national labs. There's what's called a multi-mission lab, which INL is one, as opposed to single mission labs. There's some labs that focus more on fundamental science. Marianne mentioned we are an applied research lab. There's labs that focus on national security and energy. We do both, but our focus is on energy. They range in size from a few hundred employees to over 15,000. We're at about 6,100 people. Collectively, the National Lab System, I think, employs about 50,000 people. But it's a research system that we're part of, and it's really exciting to be able to leverage the capabilities at all the national labs. So as I mentioned, we are a multi-mission lab. We do research in nuclear energy, primarily fission, as Shannon mentioned, but we also do work in fusion, other clean energy technologies that Shannon mentioned, batteries. As I mentioned, I actually came to INL to do bioenergy research, hydrogen research, and critical infrastructure protection and cybersecurity, all which interweave with the research we do in nuclear. So we have about $2 billion in annual budget between the energy side and the security side at Idaho National Lab. We're actually celebrating our 75th anniversary this year, which is really exciting. In that time, we have demonstrated 52 reactors on our 890 square mile site, 4 of which continue to operate today. One is the Advanced Test Reactor, which is the world's preeminent materials test reactor. So those 4 operating reactors are among the extensive capabilities we have at Idaho National Lab. In addition to the reactors, we also have what's called post-irradiation examination capabilities. So you can imagine after you expose fuel or a material to a extreme environment that you find in a nuclear reactor in terms of temperature and ionizing radiation, you're going to be interested to learn how the properties of that material or fuel have changed as a result of being exposed to the environment. And we have all of those capabilities in-house, a variety of different types to look at properties from the atomistic scale to the engineering scale, very specialized personnel and facilities to do this. And so you can imagine that there's very few entities that could afford to develop these billions and billions and billions of dollars of capabilities. National labs is one of the very few places. However, industry, academia, and other national labs, other parts of government even, can leverage these capabilities that we have. And Christine can talk more about the Gateway for Advanced Innovation in Nuclear program. We have other programs such as the Nuclear Science User Facilities that enable people to access these facilities, as well as the National Reactor Innovation Center. So we also have test beds, and I can talk more about that if there's interest, but in particular, there's 2 under development that are going to be ready to be used by advanced reactor developers in the next few years. And these are very unique test environments that allow these advanced reactor developers to actually come in and test their systems or system components in a highly controlled, instrumented environment, and they can actually collect information that could be used for licensing with the Nuclear Regulatory Commission. So again, a very unique offering that we in the National Lab System has that enables other people to benefit from our capabilities. So I mentioned we've demonstrated 52 reactors in the last 75 years. In the next few years, we will be demonstrating reactors 53, 54, and 55, which is very, very exciting. It's been over about 50 years since the last new reactor was demonstrated on our site, so there will be a tremendous amount of learning that comes from demonstrating these reactors that many will benefit from. So the first, I'll mention them all very briefly, is the Marvel microreactor. So this is led by the Department of Energy. It's, of course, going to be demonstrated at INL, as are the other 2. And again, a huge part of the demonstration of this reactor is just even going through the process of demonstrating a reactor, which hasn't been done in such a long time. Another reactor I wanted to mention is the Pele reactor, which is led out of the Department of Defense. And so an important feature of this reactor is that it can actually be deployed on trucks and set up in remote locations, say. One feature I want to mention about this reactor is the fuel type it uses, which is what's called an accident-tolerant fuel, and it's what's called a triso particle fuel. And what's special about this fuel is it was actually developed in the National Lab System, INL, in collaboration with other national labs and other partners. But this fuel type went from conception all the way to the point that it's being used in advanced reactor designs today, which is extremely exciting. It's a very a great success story of the National Lab System and the impact that we can have. So not only is this fuel type to be used in the Pele reactor that's going to be demonstrated on the INL site, but in other advanced reactor designs as well. So really exciting stuff there. The third reactor I wanted to highlight is the molten chloride reactor experiment, which is a uranium chloride reactor where the fuel is actually mixed in with a molten salt. So as opposed to the pellets that were mentioned earlier, or a triso fuel particle, which are kind of discrete packets of the fuel is among this molten salt. And this is an industry-led project with Southern Company and TerraPower that INL is collaborating on. So in addition to these demonstrations, INL is supporting a lot of advanced reactor developers through the various programs and expertise that we have to help them be successful in their advanced reactor demonstrations. And with that, that's where I was going to stop.
Okay, great. Thank you to all 3 of you for providing all that fascinating background information. And there's on the order of 30 questions in the Q&A already, almost. So we'll get to some of those. And I think some of those questions also illustrate the fact that there are many, many nuances to using all these the energy systems of the future. And it's difficult to cover them all in a short period of time. So let's start with a softball question, though. And this is actually in the Q&A as well, but I'd already thought to ask about it. And that has to do with nuclear around the world. So the rest of the world is also, we are not alone. We are the world's leading nuclear country, but we are not alone. And the rest of the world is moving out on new nuclear. So I'd like to ask Shannon to take this one to begin with. So what is the rest of the world doing in new nuclear? How does the US fit into it? Why is US leadership in nuclear energy technology important, both for our national and our economic security? And then from the chat, they mentioned SMRs are being pursued by other countries besides the United States. Where does the US stand relative to other countries in technology development for small nuclear, new nuclear, and at what TRL level are US reactors and international competitors? So that's a big question for you, Shannon, but why don't you take a crack at it?
Well, I'll get started, and I'm sure we'll have some additions from at least Christine here. She's been looking at a lot of these interest areas as well. I do have an opportunity within my role to engage a lot with the international parties looking at nuclear alongside renewables to advance their energy technologies and grow out their capabilities. So I would say globally, there is certainly strong interest in developing advanced nuclear, both in existing nuclear countries, as well as newcomer nations that have never pursued nuclear before, trying to leapfrog some of their technology development areas and really skip over adding just additional fossil fuels and go to clean energy generation, recognizing that renewables can't do it alone, and they want to look at a very broad suite. Many of these nations are looking to small modular reactors and microreactors, and the development of these technologies is really what's helping them move forward. There are several African nations, for example, that simply don't have a grid infrastructure that can support a gigawatt scale system, but going into those systems that might offer a few hundred megawatts or even on the tens of megawatt scale opens that opportunity to them to look at how they can bring this reliable clean energy source into a number of applications in their countries. I would say broadly, these nations are looking at applications for the electricity sector, but also looking to the harder to abate sectors of industry and transportation that I mentioned. Holistically, hydrogen is probably the primary focus across all of these nations because it is a key energy carrier and an entry point to getting into chemicals and metals and fertilizers. And so there's a lot of focus and a lot of collaboration on the nuclear production of hydrogen area. I could list out at least half a dozen different bilateral and multilateral arrangements that allow these nations and these research organizations, as well as private industry, to come together to share learnings, to share approaches with a goal of accelerating technology development and advancement to increase that TRL scale of these advanced reactors. I'll note that a couple of other high priority areas, depending on the nation and the needs of that nation and region, are district heating, using nuclear technologies, as well as water purification, desalination in some of the very water scarce regions of the world. With regard to national security, yes, there are many countries looking to nuclear energy development. The US is a leading country, UK, France, Japan, Korea. All of these nations are developing technologies, and there's a number of private sector developers in each of these countries, but the others that are developing them are Russia and China that are not traditional allies of these traditional nuclear nations that I mentioned elsewhere. And we need to think about nuclear not as a short-term partnership with a new country that's looking to new technologies. This is an 80 to 100-year relationship, as Christine pointed to, with the duration of these plants. So we need to think about those partnerships, and we want these new to nuclear countries looking to the US and our allies in establishing these relationships, because having that energy source doesn't just provide domestic energy security, but it dramatically impacts the geopolitical landscape and geopolitical security. So we need to think about the implications of this and how we partner and where we partner, because if we step back and choose to no longer lead in this area, there are others that are ready to step in, and we need to make sure that we maintain that leadership. From the interactions that I have, I see many of these countries, both established and newcomer nations in nuclear, really looking to the US to maintain and follow through with that leadership in these technologies. And the labs are stepping up to do that. We see the importance. We see the importance in industry as well. And that's something we need to continue to do. I'm not going to venture on the TRL levels. They are widely ranging because we have so many different technologies. We have advanced reactors that build upon the existing fleet of reactors and are very high TRL. They just need to get to that actual deployment stage. They're using similar materials, similar designs, but on a smaller scale. But then we can look at advanced technologies like gas-cooled systems, molten salt-cooled systems, sodium and other liquid metal-cooled systems that have a range of TRL development overall, many of those being in the TRL 4 to 6 range, and need to get over some hurdles with regard to full system demonstration and scale up of those systems.
Thanks, Shannon. Does either Christine or Aaron want to add anything to that discussion?
I do, Marianne. I think just very quickly, GAIN is primarily focused on what we do domestically in the production of a new nuclear fleet. And we do that to capture the export opportunity that is here that Shannon was talking about. And many of the projects that you see, especially in Eastern European countries, they are currently partnering with US companies. They're partnering with Westinghouse and NuScale. And these are the companies that are developed here. Some, Westinghouse in particular, built a significant amount of fleet across the globe as well. So, and in terms of leadership and I would say preservation of our nuclear expertise and leadership, it is so important that we build new fission reactors such that we have the expertise. We are close with fusion, but we are not there yet. And we want to make sure that we're maintaining our nuclear expertise to be able to support fusion when it's ready to go into the engineering and the commercialization of those plants as well.
Great, thanks, Christine. I might try to keep you on the hook. We have a large number of questions in the chat related to the economics of nuclear and the interactions with industry, and how can we get new nuclear built at a competitive cost rate in this country. So do you want to take a crack at answering that for us?
Oh, well, not to make a bad joke, but that is the billion-dollar question. So it is kind of a bad joke. So there's a lot of things that are underway. We have 2 large-scale demonstration projects going on in the United States. If you've Googled nuclear energy, you've probably heard of TerraPower, which is leading a project in Kimmer, Wyoming, and it's called the Natrium Project. One of the things, if you want to look in terms of TRL level, they have a page where they tell you what equipment they're buying next. That gives you an idea of how far along they are in the design. They just broke ground to start their construction. And what that means is they have finished a lot of their environmental permitting that's necessary for any industrial project, including nuclear. The interesting part of what they are doing is they're building adjacent to a coal station, and that does one of 2 things. One, that gives them a close connection to the grid and transmission, and use of a substation that they don't have to rebuild. The second piece that they're doing by building next to a coal station is the preservation of that workforce. So one thing that we have learned, and as I mentioned, our supply chain is worried about where the workforce will come from. Once we extend our existing fleet to 80 years, we will need to recruit an entire new workforce for nuclear energy. That can be up to 300,000 jobs that we need in our industry for a new fleet of nuclear power plants. And these jobs are family sustaining jobs. And so I spend a lot of my personal research time looking at the opportunity of building adjacent to or on brownfield sites that are helpful to these rural communities that have lost or losing a large economic contributor in their community from a fossil fuel station. The other piece in terms of the economics, so we saw while the Vogtle projects, both 3 and 4, were over budget and over time, you did see the improvements that in schedule and cost from one unit to the other. And so when you talk about learning curves, and the renewables went through the same thing, the difference is when you are what renewables has seen is as they build new, they're actually improving that technology. What we're improving on is really the project management and the mega scale capacity to build these projects. mega projects are incredibly difficult projects for not just for our industry, for every industry. We have recently updated the NREL annual technology baseline for the first time in many years for nuclear energy. So you can now go run scenarios with small modular reactors and large light water reactors that have the flexible operation that we're expecting for this new fleet of reactors. This new fleet of reactors was built with the end in mind, that it had to be cost competitive and it had to flex and be able to partner with renewables. So those are some of the items necessary. Where we are, the cost that's in the annual technology baseline is not a first of a kind cost, and it's not an nth of a kind cost. It's a between of the kind cost. And that gives us the ability to start looking at, and it gives you a learning rate as well that can be applied to their projects. And I'd be happy to share, there's other tools that have been developed around the cost perspective, but that is absolutely in our wheelhouse. The other thing that DOE just announced, it is a request for information, and they are deploying $900 million through the Office of Nuclear Energy and the Office of Clean Energy Demonstration to do Gen 3+ light water reactor technology demonstrations. And this is to really help drive down the risk for financing these projects such that we can build some of these technologies. That was a lot to pack in, Marianne. I've been trying to keep up with the questions, but I'd be glad when I'm out of the river next week to look at some of the questions and answer them on the back end.
Absolutely, great, thanks. If either one of our other panelists has anything to add on that, we can do that, or we could go on to another question. There are many different topics here. One of the things that I noticed were there are several questions about load following versus 24/7 power. So I wonder if either Shannon or Aaron would like to address that. Probably Shannon, due to the integrated energy systems. How would we actually accomplish that? How close do the nuclear reactors have to be to the other energy sources spatially, et cetera? So could you take a crack at that?
Sure, I'll get started on that. So number one, I want to dispel a myth that existing fleet reactors can't and don't operate flexibly, because that is a myth. In fact, we see significant flexible operation of the plants in France. At one point in time, they were about 90% nuclear, and that drove the need to flexibly operate to follow the load, the demand on the grid. They accomplish it using a special type of control rod in how they operate up and down in their power levels. US plants can also operate flexibly. We use a different type of control rod that establishes different limits on the rate of power increase or the rate of power decrease. And we need to understand where we are in the fuel cycle, but we can and do operate flexibly. In fact, in the Midwest region, when we started seeing more and more renewables coming online, we started seeing some grid congestion in regions. Some of those plants in the Midwest actively began operating with what was referred to as advanced economic dispatch, meaning they would down power to accommodate other generators in the grid such that they weren't selling electricity at a loss or simply dumping power. So number one, our current fleet can, within constraints, operate flexibly. So with that said, when we look to advanced reactors, some of these advanced reactor designs are much more nimble. Fast reactor, meaning the spectrum at which it's actually using neutrons to produce fission, changes how rapidly it can be responding to changing demands. So those are things that we can do, and you'll see a wide range of those operational limits for the different types of reactors based on those designs. When we think about whether or not that makes sense to operate flexibly, well, that's another question, especially when we look at the reason for that flexible operation. If it's very predictable changes in the load, like weekly, monthly, seasonally, we can predict that and we can build that into our overall refueling cycles and plan for, instead of maybe a 1.5-year cycle, a 2-year refueling cycle. But when we have highly variable generation that we are accommodating within the grid, we don't have good forecasting tools yet to allow us to build that into our fuel cycle planning. What that means is we may still plan that same refueling outage regardless of how much that plant is flexibly operating, and thus reduce our utilization of that very valuable nuclear fuel asset. So other ways to do this are what I was talking about. Instead of flexibly operating the power in a load following mode, I like to think of a load dynamic mode, where we can use ways in which we shift that heat, that steam, from going to power production to going to a thermal energy storage system, or going directly to these industrial applications. In fact, one of the advanced reactors, Natrium, the one that Christine mentioned, will be put in at Kemmer, Wyoming, is designed to have that integrated thermal energy storage component as fundamental to their system design. Initially, they will be deployed just to support the grid, but that gives them the capability to offer peak power when renewables may not be producing as much, or there's a reason that power demand has increased. We have a significant weather event, but it also enables them in the future to use that thermal storage as essentially a thermal management system, such that that energy that's in that thermal storage system can be directed to power conversion, or it can be directed to a plant that's taking coal resources and converting that carbon feedstock into higher value products like polymers that we use in our daily lives. So it's a matter of how you design that interface, that integration, that gives you those different levels of flexibility. And in a sense, you can start thinking about storage as small capacitors in the system that hold it for a little while and give us a way to establish a switch between delivering to electricity or delivering to heat users or to hydrogen production. So I hope that answers the question at least somewhat. There's a lot of nuances in how you actually accomplish that, depending on the system that you are implementing. And I'd be happy to follow up further with those if anyone wants to reach out to me by email.
Okay, great. Thanks. I'd like to direct a question to Erin about the labs in general, just to take a little break from the 52 or 55 questions we have in our Q&A. But why is it important to have the U.S. national labs engaged in the technology and demonstration for nuclear? What do we bring to the table that industry doesn't, or how, why is it better for us to partner with industry and just instead of letting industry do it all? And there's 17 labs. Are there other labs besides Idaho? And of course, we all know the answer to that, those of us who are from the lab system, that are important for new nuclear, and how do they complement the capabilities at INL? And then a lot of questions in the chat also about, what about fusion? And INL is primarily a fission lab, but as you mentioned earlier, Erin, INL does do a little bit of fusion. And how does fusion fit into sort of this overall picture as we move forward in the R&D landscape? So not much for you to address there, but go right ahead.
Yeah. Yeah, well, I touched a little bit on the capabilities INL offers as a national lab, and that these capabilities are accessible to industry, to academia, to other national labs, to government entities. And it would be very difficult for any given company to build these billions and billions and billions of dollars of capabilities. So by having national labs invest in these capabilities and have them available for other people to learn from, there's many people that can benefit from this government investment. So that's a really important role the national labs have to address these questions that are for everybody's benefit to have answered, especially in the energy space. So I mentioned a couple examples. The program that Christine leads, the Gateway for Advanced Innovation in Nuclear, is one option for people to access the national lab capabilities. Not only INL, it's a DOE program, so other national lab capabilities. I can highlight a few examples of those in a minute. We've got the National Reactor Innovation Center that is building test beds, is one of the examples of the many things that they do. Another example of something that they're doing that all reactor developers can benefit from is look at ways to reduce construction costs, for example, and that's something that everybody can benefit from. So we use national lab expertise experts from across the national lab system to generate information that everybody can learn from. And then I mentioned the nuclear science user facilities that, again, are facilities not only in the national lab system, but in universities that DOE has brought together as a capability offering that people can access through a voucher program. So the extensive capabilities of the national lab system, not only INL, but all of the 17 national labs, can be accessed through a variety of mechanisms. And then there's always just research partnerships, proposals that we collaborate on, and projects that we work on together. So these facilities are highly used by a variety of different interested parties. And so in terms of collaboration, of course, the National Energy Technology Lab is among our favorite collaborators. We do a lot of work in that space with your national lab, including in AI as one example of the areas that we're working together. Argonne National Lab, we have strong capabilities in modeling and simulation, among other areas. Oak Ridge National Lab has extensive materials and fuels capabilities. They have the high flux isotope reactor. They also have a lot of expertise in fusion, so we work with them on that. So it's really important that we leverage all these capabilities across the national lab system, because each of the national labs has their own specialty. And if we don't take advantage of these collaborations, we'd be missing out on so much opportunity to advance energy technologies. Los Alamos National Lab, we do a lot of collaborations. One example is space nuclear. Lawrence Livermore National Lab, again, we do fusion collaborations. If you've ever had the opportunity to see the National Ignition Facility, NIF, which I visited with Marianne, please do. It is remarkable. One of the very impressive capabilities we have in the national lab system, but that one is pretty good. Sandia National Lab, we work with them on cyber nuclear research, and certainly beyond that, even beyond nuclear, there's a ton of collaborative opportunities between INL and the other national labs. But fusion is definitely a space that we are growing at INL. We've been working in the space for a while now, specifically focused on tritium and how that interfaces with different materials. And so we have a lot of materials expertise that we can leverage to grow our fusion capabilities. And so that's one benefit of having a diverse multi-mission lab, is that we have a variety of experts that have diverse backgrounds that we can leverage to build diverse collaborative teams. And of course, we have university partners that we're working with in the fusion space, and some of the national lab examples that I gave. So fusion is certainly a very exciting area, and it really offers us to build on the fission capabilities that we've had 75 years of experience in. And yeah, definitely a very exciting emerging field.
Yeah, great. Thanks, Erin. We only have a few minutes left, but we've had quite a few questions in the Q&A about safety and regulation of nuclear power, and how important that is for public perception, and the role of the U.S. Nuclear Regulatory Commission in safety, but also in the speed of deploying new nuclear. So I'd like to throw a sort of a general question out to whoever would like to take a crack at this one with regards to regulation. I thought it might be Christine. And
Yeah.
say a few words about speed of getting new nuclear and the importance of safety, and why is continuing to keep older nuclear plants on the grid? Why is that safe? How can we be assured that that is safe? So over to you, Christine.
Oh, okay, you don't ask any easy questions, Marianne. We love that about you. All right. So here's the thing. The way you want to think about safety and the Nuclear Regulatory Commission is not that they are responsible for safety. The person who designs the plant is responsible for safety. And what the NRC is responsible for is writing the rules by which they can ensure that the plant is safe. So the equivalent to that is the same way your cars get designed, the same way airplanes get designed, right? So you have people that are responsible for designing them, and they submit those designs to ensure, or they test them to ensure that they meet the rules that have been written. So with that, our NRC is doing, I think, first of all, they have been the gold standard for nuclear regulation across the globe since we started using nuclear for a commercial power use. So across the globe, the NRC has partnerships helping other nations develop their regulatory program. In North America, they have developed a strong partnership with Canada. This is important because what they are doing is if there is a design under review in Canada, we have US NRC staff also participating in that review of the design. So if that design was to show up and be submitted to the US NRC, we are ahead of the game. And they're even looking so far as to how the same design package could be submitted. The safety record for our existing fleet is tremendous. It's not to say that we haven't had accidents, and I realize this is a really poor time to bring up that subject because we're out of time. However, the safety record of our plants is bar none for the amount of power that we produce. The most excellent, I feel like Bill and Ted, the most excellent safety record. The last thing I'll say is the NRC has been meeting their commitments. So when we have had developers submit their applications, they're given a review time. Typically, that's anywhere from a year to 2 years. But the NRC has been meeting their schedule. And I think while we might all want the licensing process to be faster, you can manage around someone that's meeting their commitments. As a project manager, I think we've all been able to handle that type of thing. If you know when you're getting your answer, you can manage your team to that endpoint.
Right. Thank you, Christine. We are out of time, so I think I'll turn it back over to Maria at this point. It's been a great honor to lead this discussion, and I want to thank all three of our great panelists.
And I would echo that thank you to all of you, including Marianne. Thank you so much. You could just tell by the number of questions people were very interested. So I do want to wrap this up. I want to thank you all for attending. Thank you to the panelists. And for those of you who have signed up for the discussion session afterwards, just a reminder, you have to leave this session and use this separate link to sign in for the discussion session after this. So thank you again, panelists. So much to talk about. Maybe there'll have to be a follow-up. But anyway, thanks everybody for coming and thanks for the panel. Thanks everybody.
Bye.
Bye.